Okay, section 3.5, we're going to be talking about limits again, but it's from a little bit different perspective than we talked about limits back in chapter 1. These are going to be limits that are considered limits at infinity. So let's talk about what that means. So we're going to let L be a real number. The statement, the limit as x goes to infinity of f of x equals L, means that for each epsilon greater than 0, there exists a capital M greater than 0, such that f of x minus L is less than epsilon whenever x is greater than m. There's the reverse statement of that, number 2. Again, the statement as x approaches, this time it's negative infinity of f of x equals L, means that for each epsilon greater than 0, there exists a capital N less than 0, such that f of x minus L is less than epsilon whenever x is less than n. I think it was Kayla that had asked me, but it may have been somebody else. What are we going to have to memorize for this test? Was it you, Kayla, or somebody else? It was David. Okay, so this isn't it. We're not memorizing. There's no memorization for this exam, okay? So I've asked you on exam number 1 and exam number 2 to actually flat out memorize something, and this looks like one of those things that I might do that with. I'm just letting you know it's not. There won't be anything like that on this test, but it should feel like something you've seen before. Have we seen a statement like this before that I did ask you to memorize? Yeah, it's very similar to that, right? And so this is actually talking about what happens on the ends of the graph. If x is going to infinity, sort of graphically speaking, what that means is that we're going to the right side. That's not good. Let's try that again. We're going to the right side forever, right? We're moving this direction and this direction and this direction, and we're moving to the right forever. That's what's happening as x goes to infinity. And if we're looking as x goes to negative infinity, then we're going to the left forever. And the question is, as we move to the right or to the left, is there some value that we get close to, or is there not, right? Does this graph look like something that sort of tapers off at what we would have called a horizontal asymptote back in algebra, right? That's what they are, but that's where you saw it, was about horizontal asymptotes. Or does it just shoot up to infinity or down to infinity forever, right? That's the question that we're asking. So if it has some sort of a tapering off feature, some horizontal asymptote feature, that's the m and the n that it's talking about, right? The m and the n are these locations that beyond that, it gets infinitely close within epsilon of where we're talking about. So let me draw a little bit more descriptive a picture. Actually, I'll just draw it on the side. I won't redraw this one. So if I had something that looked like, that's not great, something like this, then what it's saying is that there's some location, and we'll call it m on the right. If we were doing this on the left, we'd call it n, just for a different letter. That if we get beyond m, right, if my x value is somewhere further along, that I'm closer to that horizontal asymptote, whatever that limiting value L is. I've drawn it here like it's the asymptote that's the axis, but let me actually draw it one more way, just shifting it up so that I can actually draw it in a little bit. There's some asymptote line here, like this. We'll call it L. And we get infinitely close to that so that the m value is actually bigger distance away from the asymptote, right, than it was when I was at the x value. So this point right here and this point right here, I'm getting closer. The epsilon's getting smaller, right? The distance away is getting smaller, and that's all that this is describing. So what we're going to be really looking for in this section is something you've done before. It's horizontal asymptotes. That's what it means to have limits at infinity. It means there's a horizontal asymptote. But we're going to be doing it from perspectives of things that maybe you didn't see done, or ways you didn't see done in algebra. So horizontal asymptotes are these lines y equal L. So that the graph of f, when the limit of x as x goes to negative infinity of f of x equals L, or if we do it from the positive side, the limit as x goes to positive infinity of f of x equals L. So you can have a horizontal asymptote that's only a horizontal asymptote on one side. That's a possibility. It could be a horizontal asymptote on both sides. It could actually be different on the left side and the right side, depending on how the function is defined. So we have all of these different options, and these would be horizontal asymptotes. Now, the primary thing that we're going to make use of as we look at these horizontal asymptotes is our next theorem. Okay, it's theorem 3-6. I think that's what it was used to be called, and I think I changed it because your book keeps changing numbers when we change additions. So mine actually says 3-6, or 3-10, excuse me, yours doesn't. These are limits at infinity. If R is a positive rational number and C is any real number, so C can be any constant value, then the limit as x goes to infinity of x to the value r, C over x to the value r, is equal to 0. Furthermore, if x to the r is defined when x is negative, then the limit as x goes to negative infinity of C over x to the r is also equal to 0. So jot that down and we'll talk about what it's actually telling us. Okay, this is telling us that anytime you have a number, just a constant, divided by a power of x, okay, it says R is a positive rational number. It has to be positive. It doesn't have to be a specific size. It doesn't have to be a specific type. So it could be a fraction. It could be a decimal. It could be a square root itself. It could be an integer, right? It could be like a 7. That's okay. But anytime you have x to a power in the denominator with a constant on top, then as you go to the right forever or as you go to the left forever, you're going to end up with a limit of 0. That's really helpful. Now, it's really helpful if the function just looks like that, right? So if I just gave you a function that just said something like, and we'll use one that you're familiar with, 1 over x squared. Okay, well that fits. I got a constant on top. I have x to a power on bottom. That power is positive. It's going to fit with this description. You may have a remembrance of what this basically looks like. Let me get my thing back up on solid. It looks like this. So sure enough, as you go to the right forever or as you go to the left forever, right, it tapers off at the x-axis. That's a y value of 0. It's a limit of 0. But what this is telling us is that this is the basic shape on the ends of the graph, whether it said x squared or whether it said x to the point 2. Or whether it had a 7 on top or a negative 2 on top, right? It doesn't matter what the number is on top, and it doesn't matter what the exponent is on bottom as long as it's positive. It's going to have this behavior, these features on the end of the graph. So our goal as we work through these problems is going to be to try to get our functions to have this form, because this form is something we know about. Okay? Now, if you take a look at the first one, they're actually going to lead us through a couple of different examples of what happens or how things change depending on what our function looks like. So they give us an f of x. It's 5x cubed minus 3x squared plus 10x. And they're telling us on part A that we're going to define a function that takes that f of x and divides it by x squared. So we're actually going to write that down first. I have 5x cubed minus 3x squared plus 10x divided by x squared. That's my function for part A. And we're going to do some algebra simplification, which we've done this kind of algebra simplification when we did derivatives. And so instead of writing it like this, it might be a little bit more helpful to think of it, whether you write it this way or not, but to at least think of it as the x squared dividing each piece of the numerator. Okay, is that okay? That's an application of fractions. We're using it sort of in reverse of the way you've typically used fractions in like middle school and high school. But it's true, right? I can separate it like that. And then I can do some reducing. So what happens with my 5x cubed over x squared? What do I get from that? I just get 5x. So the x squared is going to cancel with two of these x's that are on top, so I have 5x. How about my 3x squared over x squared? Yeah, I have just the 3, and there's a subtraction sign in front of it, so I'll have negative 3. What would I do for the 10x over x squared? Yeah, I would get just 10 over x. So one of the x's on the bottom would cancel with the x on top. Now, the piece at the end, the 10 over x, that looks like this form, right? I have a 10 on top, that's a constant. I have an x on bottom, that's my x. Its power is not exactly exciting, but it's a power of 1. So it fits the criteria. So this piece, if I'm going to infinity, because that's what it says I'm going to do with the directions up here, right? That piece at the end is going to go to 0. But think about what happens to the earlier pieces, okay? So what I'm trying to find now that I've separated these pieces all out is the limit as x goes to infinity of 5x minus 3 plus 10 over x. And what we learned in chapter 1 is that we're able to separate these out into individual pieces. We learned it for limits as x goes to a constant, but it works just fine for this as well. Right? These are the pieces. And so this piece is 0. It fits the theorem that we had on the previous slide. But what happens if you plug in numbers that are getting infinitely large into 5x? Yeah, it's going to keep going up and up, right? Like say you did 5 times 10. Well, that's 50. What if you did 5 times 100? Well, that's 500. And you did 5 times 1,000. That's 5,000. It's going to get bigger and bigger and bigger. This piece at the beginning, the very first piece, is going to infinity. Do you guys see that? This is infinite. What would happen, because we'll see some of these happen later too, this piece in the middle, what happens as x goes to infinity for the limit of 3?
It doesn't go up.
It doesn't change, right? 3 is a constant horizontal line. It never changes. No matter what number is x, there's no x to plug it into. It's going to give me back a value of 3. So this piece here is 3. So in some sense, what we've actually got here is infinity minus 3 plus 0. Well, what happens when you take infinity and you add or subtract something to it? It's still infinity, right? Did you ever have those discussions when you were a little kid with a parent or a relative, like a grandparent or something like that? I know my children did, my daughter especially. She would say things like, I love you to infinity, right? Right? And you'd say something like, I love you to infinity times 2. Well, that's still infinity. It didn't change the size, right? This didn't change the size. I don't care what you're adding or subtracting from it, as long as they're constants, which they are here, they don't change it. It's still infinite. So the answer to this one, part A, is that this is an infinite limit. Okay, everybody good? Okay, we're going to change the constraints a little bit, though. Instead of dividing by x squared, we're going to divide on part B by x cubed. So everything stays the same except the denominator is the x cubed now instead of the x squared. And just for some space saving, because I ran out of space a little bit on my last slide, I'm going to write it over here on the right side. So this is 5x cubed still, minus 3x squared plus 10x. And I'm dividing by x cubed. If you want to see each piece written out over x cubed, you can do that. I won't do that on this one since I did it on the last one. We'll just do it piecewise. What happens when I take 5x cubed and I divide by x cubed? You get 5. How about the negative 3x squared divided by x cubed? It's going to still be negative. 3 over x, right? The x squared that's beside the 3 on the top will cancel with 2 of the x's on bottom. And then I have 10x over x cubed. Right, 10 over x squared. Okay, everybody good? So that's the function h of x that I have. And I want to take the limit of it. So I want the limit as x goes to infinity of 5 minus 3 over x plus 10 over x squared.
And then it's just going to be 5?
It is just going to be 5. How come, David?
Because 3x and 10 over x to both equal, the limit both equal to 0.
Right. Now, again, if we wanted to write it out sort of like longhand, we'd write it like the right-hand side of our last problem. Okay? That's what we would do. We're not going to write it out on this one because you've seen me write it out once. If you want to see it written out each time, by all means, please feel free to do so. But what's going to happen is that this piece stays 5. This piece goes to 0. And this piece goes to 0, right? Those last two are in the form of our theorem that we have, right? 3 over x, 10 over x squared. They're a constant over x to a power, positive power. The first piece is just a constant, so it does not change. So the whole limit, as David said, so I've really got 5 minus 0 plus 0, right, is 5. What I'm dividing by between part A and part B really mattered, right? It mattered what that value was. It changed the outcome drastically. Now, can you confirm this with your calculator? Well, of course you can. Grab your calculator out. Let's graph both of these and see that it makes sense that what we're getting is what we're supposed to be getting. So back on the first part, part A, let's just put it in exactly like it was given to us, right? 5x cubed minus 3x squared plus 10x over x squared. Probably a standard window will be okay. I'm trying that. We'll see. If I'm wrong, we'll fix it. Well, it's not showing anything in my standard window. Let's see. What were my equations? This. Okay, after you do a standard window, if you'll do zoom fit, it'll change your y-axis to be more helpful. So zoom fit is zoom 0. And you should be getting a graph that looks something like this. Does your graph look like that? If it doesn't, yeah, yours does. Y'all's okay? No. Oh, it's just because it's wider. Yeah, so your window is, if you hit your window, mine went from -10 to 10. Try -10 to 10 here. It'll shift it a little bit, look a little bit cleaner. Are you still working on yours?
Yeah.
Yeah, do an x min, x max of -10, 10. That works pretty well. And then hit zoom fit. Yeah, you've got that one. How are y'all's? Okay, let's look at it. Y equals. Okay, we want to put all of it in parentheses. And then divide by the x cubed, or x squared of the denominator. You're still working on yours. Graph, good deal. Very nice. Okay, as a few of you are still finishing up the graphing for it, notice what happens as we go to infinity on the right, because that's the question. This gets infinitely large, right? Yeah. Is there a problem on his? Ooh, hit y equals. You got x cubed. Try the x squared. We're going to do x cubed in a second. Yeah. Did we get it over here? Yeah? Yours looking right. I think you're doing divided by x cubed right now. Hit y equals. Did you do x squared? Try it. Hang on. I just think your window is not big enough. That's why you're not seeing it. -10 to 10.
Okay.
And then do zoom fit. Here we go. All right, did it work, Andrew?
I think I put the equation wrong. Yeah.
Okay, I think it will if you
Yeah,
change,
that's
adjust your window a little bit. Okay, so everybody good on this one? Okay, So let's do the same thing now. Within your window, just change the denominator to say x cubed. Some of you actually put that one in first. And let's see how it changes our graph. Oops, looks a lot like the graph I drew earlier for our previous problem. To adjust, does your graph look something like that now? Okay, so notice if you went to infinity, right, as your x value is getting infinitely large, this one is tapering off. It's hard to see that it's tapering off at 5 because my window is not very good, right? If we adjusted our window a little bit, it would look better. So right now, I'm going to guess, so like my window is going really high. Let's just see. Yeah, my window goes up to 48. If I were to adjust it so that my y minimum is 0 and my y maximum is, say, 20, I think we would see that it was tapering off a little bit better. And in fact, we do. So the graph actually ends up looking more like that if I change my window to be a little bit tighter fitting, and it looks like there's a tapering off, at least the right-hand side, which is what I'm looking for, is at 5. Okay, are we good with that? Okay, so confirming with your calculator, it's a pretty good idea. Make sure that you didn't make an error in your judgments along the way, right? Not a bad plan. Okay, so I want to look at a few examples more that are unique. So if it's a polynomial over a polynomial, we can separate out. We can do this all day long. Okay, they never change. They look like this. I don't care what the numbers are on top. I don't care what the exponents are. They don't even have to be polynomials, right? I could have x to the 3.5, which is not a polynomial, and we'd still have the same sort of thing fleshing out, right? All of the things would be the same as a general statement as what we've done. But not all problems have just a constant on top when we do these divisions. So take a look at number 2. So on number 2, we have polynomial on top and a polynomial on bottom, but the part that's on bottom has addition and subtraction in it. And nothing over here talked about having more than one thing in the denominator, did it? It looks like I'm supposed to just have one piece in the denominator, but then I get to a problem like this and I have 2 pieces in the denominator. Clearly that must be doing something different, or we wouldn't have had that theorem that was so specific to having just x to a power. So what do? Well, what we're going to do is we're going to first identify what is our largest exponent for x in the problem. What is it on this one? 3. Okay, so our largest exponent here is x cubed. Everybody good with that? Okay. So whatever your largest exponent is, what you're going to do is you're going to multiply the entire numerator and the entire denominator by 1 over that exponent. Well, that variable to the exponent, 1 over x cubed. Okay? The limit stuff's going to come along. We're not going to change any of that until we actually deal with it. So every single time we're going to write limit x approaches infinity. But we're going to distribute this fraction across each piece of our numerator and denominator. So I have a 1 over x cubed times 3. That gives me 3 over x cubed. And I'm going to distribute the 1 over x cubed to the 2x. If you need to write it down as 2x over x cubed and then simplify it, please do. If you don't, because you see that one of those x's is going to cancel anyway to give you 2 over x squared, then you can do that. So this x is going to cancel with one of these, leaving me with 2 there. I have a 2 over x squared when I distribute it there. The next piece in the denominator now is to distribute the 1 over x cubed to the 3x cubed. And when we do that, the x cubes cancel, leaving me with 3. Right, 3x cubed times 1 over x cubed cancels my x cubes, leaving me with 3. And the last piece is just multiplying by 1, so that's just 1 over x cubed. Okay, so we had a property of fractions way back when we learned about fractions, and you probably learned about them first time in upper elementary school, maybe early middle school. And it said that as long as you multiply the numerator and the denominator of a fraction by the same thing, you haven't really changed the fraction. You changed what it looks like, but you didn't change it, right? Because 1 over x cubed over 1 over x cubed is equal to the number 1. We're allowed to multiply by 1. It doesn't change values. But notice these pieces. Now, this isn't super friendly if we were doing things like taking a derivative. I don't want to take a derivative of something that looks like this. This looks terrible. But for limits, this looks really good. Because notice, every piece of this looks like something here. Except for the constant piece. The constants are easy. We dealt with them here, right? When I had a constant of the 3 here, it's it's limits just itself. Limits of constants are themselves. So constants are really good, and constants over and power of x are really good. And that's all I have present in the problem here now. So this piece, I'm going to write this one out fully, and we won't write it out on necessarily every problem. But this actually means now have the limit as x goes to infinity of 3 over x cubed minus the limit as x goes to infinity of 2 over x squared over the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 1 over x cubed. Right? We're taking the limit of each individual piece. And we had a property back in chapter 1 that said we can do that. Right? If we have the sum and difference of things, we can take the limits of all the pieces. We have a property that allows that. But what is the limit as x goes to infinity of 3 over x cubed? It's 0. Right? This whole thing is 0. What is the limit as x goes to infinity of 2 over x squared, It's another 0. Now don't get too carried away and miss all the pieces. The limit as x goes to infinity of 3 is 3, and we need it not to be a 0 down in the denominator, right? I can't have zeros in the denominator and the numerator. I've got a problem if I do that. And that's actually the reason that we identified that x cubed was our highest power. It's because I do need that constant piece to still be there when I'm done. Okay? And then the last one, the limit as x goes to infinity of 1 over x cubed, that one's a 0 again. So we have 0 minus 0 on top, 3 minus 0 on bottom. So I have a 0 on the top and I have a constant on the bottom. So I get a total value of 0. Could we confirm that with our calculator? Could we graph it and check to make sure that that seems reasonable? Well, of course we could. Let's do it real quick. Take the original function, 3 minus 2x over 3x cubed minus 1. And then we're going to make a connection back to algebra where you've seen a problem like this before and thought about it from a different perspective. Zoom 6 is sort of reasonably okay. It's almost too tight, to be honest, almost too small. But the graph looks something like this. It gets really tight to there really quick, so if you were to zoom in, it would be a little bit better, but it looks something like this. It's shifted over a little bit. Okay, does everybody's graph look moderately like that? Okay, good. So here's what you saw in algebra. Probably an Algebra 2 course, maybe a college algebra course, depending on the sequencing you took. I'm going to go back up here and clean off a little bit of what I've drawn in with my arrows so we can look at it again from that perspective. What is the highest degree, that means exponent, of the top? What's the degree of my numerator? Biggest exponent? 1. The exponent on top is a 1, right? This top has a degree equal to 1. What's my biggest exponent on bottom? We identified it earlier.
3.
It's 3. In college algebra, our college algebra that we teach here, and in high school algebra 2, there's a property about horizontal asymptotes that says if the degree on the top is smaller than the degree on the bottom, then the horizontal asymptote will be y equals 0. Does that sound a little familiar? If it doesn't, that's okay. But it is something we discuss from that perspective in algebra. And we see it present here. The degree on top is 1, smaller than the degree on bottom 3. And our horizontal asymptote is, in fact, the x-axis or the line y equals 0, which means my limit that I'm looking for will also be 0. Okay? If you don't care to remember what I just said, it's not going to hurt anything. I just want you to know it's consistent with what you've done in the past. Now, 3 looks a little different. What's different about 3?
It's all constant. No, it's variables.
There's variables in everything. That's one thing. What else? There's a square root involved. And I didn't really do anything with square roots, right, in terms of my descriptions of things before. Please remember that you cannot just, sort of distribute the square root to each piece. That does not work. I'll give you an example of why, because somebody's going to want to try to do it anyway, because it feels like something we would wish were true. Let's say that we had the square root of 9 plus 16. And let's just try. If I were able to do this, what's the square root of 9? 3. What's the square root of 16? 4. Okay, we would get 7 if I were able to distribute my square root, right? What is 9 plus 16? 25. What's the square root of 25? It's 5. Most importantly, it is not 7. You cannot distribute square roots. Okay? So we can't just distribute the square root. That's not going to work. However, I would like for you to think for a moment, if for just, the argument's sake, this piece weren't here. Just pretend that it weren't here for a moment. Okay? If it really just had the square root of x squared only, what would the exponent be if I simplified the square root of x squared? It'd be x, right? I just have x to the power of 1. So if I could do this somehow, there'd be just an x on bottom and there would be my x on top. Agreed? And the highest exponent for any of the x's in my problem would be an exponent of 1, right? Okay, so as I'm sort of thinking through, like over here I told you, hey, let's look and think about what's my highest degree of x. We're sort of ignoring the minus x on bottom and just looking at the highest degree part just to figure out what my highest degree is. Not because I'm going to simplify it in that way, okay? I'm just trying to identify what's the highest degree I'm going to be needing to use, and the answer is x to the power 1. On the last one, it was x to the power 3. Okay, so I'm erasing my scribbled out piece now. I need it still. I'm still going to be multiplying by 1 over that value to the top and bottom. But in order to multiply something that's under a radical by anything, the other thing also has to be under a radical. So I'm going to manipulate how this piece looks. And instead of having it written as just 1 over x, I'm going to write it as 1 over the square root of x squared. And I know that seems sort of silly. I mean, the square root of x squared is x. But it's necessary because one of our properties of radicals says that I can only multiply things underneath a radical by other things that are underneath a radical. So I've simply rewritten this in a way that allows me to multiply the two pieces together. Okay? It's a funny looking way of writing it that allows us to do what we want to do. So then my numerator will become a 1, right? When I multiply 1 over x times the x, I get 1. And in the denominator, I have the square root of, and I'll write it in here just because it is a little weird looking. This 1 over x squared piece gets to go underneath there now because they're both underneath radicals. So here's my x squared that was here before. Here's the 1 over x squared. And then I have my minus x also times my 1 over x squared. Okay, does everybody see where all those pieces showed up from? I'm pretty sure there's one of these in your homeworks or on a quiz or something like this that I've used in the past, which is why I want to mention it too, because it's not a difficult algebra thing to do, but it's not something we do a lot. It's a very unusual sort of convention of things that we see. Okay, so I can simplify what's underneath all this denominator now. So I have the limit as x goes to infinity of 1 over. What happens when I have x squared times 1 over x squared? They cancel out to give me what? a 1. And then this piece, what's x times 1 over x squared? That one's 1 over x, right? Everybody good? Cool. Now, if you wanted, we could do like what we did here, where we write all the limits out next to all the pieces. I showed you one of those earlier, and then I said, but we don't really need to write that every single time. Agreed? So again, I showed you one of them where we did it. Now I'm going to show you one where we're not going to, but if you feel like you would like to see that, feel free to do it. What is the limit of the 1? It's 1. Okay, and I'm just going to change colors and rewrite it out so we know that we've checked it. What's the limit of the 1 here in the denominator? It's also a 1. It's underneath the radical. I mean, so keep in mind, there is a 1 and it's still under the radical. What is the limit of 1 over x? That's 0. But that leaves me with the entire denominator underneath the radical equaling 1. So what I have is I have a 1 on top and I have a square root of 1 on bottom. What's the square root of 1? 1, right? It could have been the square root of something else, right? If instead of this saying just x squared, it had said 2x squared, right? I mean, it could have said that legitimately. And we could have had a 2x squared and there could have been a 2 here. So we could have a square root of 2 in the denominator. That's okay. But we didn't. We just had 1. And so this is just 1 over 1 or 1. The limit's just 1. Again, check it with your calculator real quick. We have the time to do so. Let's double check and make sure that that seems reasonable. If you have x on top and you're dividing by the square root of the quantity x squared minus x, you zoom 6 it, like I turned that into a verb, noun to verbs. I did a zoom 6. My graph looks a little weird, admittedly, but it looks something like this in terms of the right-hand side. It's tapering off, and in particular, we are in fact tapering off at the value of 1. And if you weren't sure, like if you're like, okay, but how did you know it was 1? Trace. Click on the trace button, okay? There's a trace button, and you can just trace over to the right-hand side as far as you want until you are convinced that that number for the y value is tapering off at 1. And mine is. I'm getting 1.04 right now, and then it's 1.03 something, and it just keeps getting closer and closer to 1, but it never dips below. So I can use the graph to confirm that I didn't make a mistake. Now, that wouldn't have worked very well if the answer was actually 1 over the square root of 2, right? I mean, it wouldn't be quite as helpful in terms of my graph. I could get a decimal approximation to see that that seems reasonable. But because this value was 1, it worked really nicely to confirm the actual number as opposed to sort of just an approximate number. Okay, we have one more. You ready? This one is unique and it's very different looking because of what? Trig. I have a sine graph. So I am going to do the problem differently. That sine graph is going to do something else. I do not have a constant on top, and there's no way to get sine of 2x to be a constant. It's just not a constant. But you do know what sine graphs look like. What do they look like?
Waveform.
A waveform. And they bounce up and down between what values? Like what y values are they bouncing up and down between on a sine graph? Negative 1 and 1. Yeah, so they're bouncing between negative 1 and 1. So the basic graph looks something like this that we're sort of describing. I keep forgetting I'm turning on my dots. And it tops out at 1 and it bottoms out at negative 1. And it keeps bouncing up and down in between. So let's think intuitively. I know you could graph it, but just think with me about what should be happening here. If I'm taking something that's going back and forth between 1 and negative 1, and I'm dividing it by something getting infinitely large, because that's what this says, right? X is getting infinitely large. So if I take this graph and I divide it by something getting infinitely large, what should happen? Any thoughts? If my peak is at 1 and my minimum is at negative 1, and I'm dividing by something that's by 10, then by 100, and then by 1,000, what should be happening?
Infinitely small.
What's that?
Infinitely small.
It should get infinitely small. So the picture should look, and if you look at your calculator, it will, intuitively speaking, this makes sense too. It should be looking like this. This isn't a good, let me draw it a little bit tighter. Can you imagine it? I'm dividing by something getting really big. So as I do, it's sort of like narrowing the focus. If you can kind of think about it like this, it's sort of, kind of focusing in like this on it. Can you picture that? It's forcing it to sort of squish and get smaller as you go. Okay, so we should expect that this is getting infinitely small and close to zero. But how do we show that without just looking at a graph? Well, we're actually going to write down a statement about the fact that it's trapped between -1 and 1. So we know that -1 is less than or equal to sine of whatever angle, this happens to be 2x, but that doesn't affect anything, is less than 1. Agreed? If I can put a function in between two numbers, what I've done is I've sandwiched it in between. This is actually an application of something called the squeeze theorem. I'm going to squeeze it to do what I want it to do. Okay? Notice the sine 2x itself, though, is not my function. My function says sine 2x over x. So my next step is going to be dividing each of these three pieces of this inequality by x. This does not change the inequality because the x value is positive. That's a property of inequalities. Somewhere along the way in algebra, you're like, why am I learning all these things about different properties? Well, because you end up using them all in the same problem. I mean, we've done 3 problems, and I keep talking about different, algebra properties, right? I am allowed to divide an inequality, and this one happens to be an inequality with 3 pieces. And as long as I'm dividing by a positive, which I am, because it says my x is going to infinity, those are positive numbers, and it doesn't change the inequality. Remember, inequalities do change direction when? When you divide or multiply by negatives. So if you were dividing or multiplying by a negative number, we would have to flip the signs of the inequalities. But we're not. It's a positive number. So this inequality stays the same. Everybody good? Okay. But again, I don't just have sine of 2x over x. I'm supposed to have the limit of this thing. So we're going to drop a limit into each piece of this inequality. So I'm going to change this now, and it's going to say the limit as x goes to infinity of -1 over x is less than or equal to the limit as x goes to infinity of sine of 2x over x is less than or equal to the limit as x goes to infinity of 1 over x. Why would I want to do that? Look at the outsides of your inequality. Do we know how to take the limit of -1 over x? Yeah. Do we know how to take the limit of 1 over x? Yeah. And what are both of them? They're 0. I have sandwiched or squeezed the limit that I care to find in between two values that I know the limit for. They're the same as well. They're both zeros. Well, if they're both zeros, what does the thing in the middle have to be do? It'd have to be 0, because it's supposed to be bigger than 0 and less than 0 or equal to on both pieces. The only possible option then is that it's actually 0 itself too. I've squeezed it with no other place to be. Right? So this limit here in the middle as x goes to infinity of the piece I'm looking for, sine 2x over x. So in math, these 3 dots, if you see them like this, mean the word therefore. Okay, that's like, it's texting language. It's like what you mean when you put like THX or TBH or whatever texting you use. WY, YW, that one's one, right? Okay, it means therefore. Therefore, the limit as x goes to infinity of sine of 2x over x is also equal to 0. And that's happening, and I'm going to actually cite it here because there's a very good reason. This is by what's called the squeeze theorem. And it works really well, not just trig functions, but specifically for sine and cosine functions, because sine and cosine functions have this trapped feature of being between -1 and 1. It doesn't work for the others, like tangent, cotangent, all that kind of stuff. We won't see any questions that are related to this topic with those. Okay? What do you guys think? It's okay? There's no derivatives. There's no antiderivatives. There's a lot of algebra. I mean, this is a lot of algebra section. All right? Okay, we'll stop there for today.